Next topic, transient response of a passive circuits by differential equation approach. Analysis of behavior of electrical circuits reveals that as soon as a circuit is switched from one condition to another, either by change of source or by alteration of circuit elements, branch currents and voltage drops change from their initial values to new values. These changes takes a short spell of time to settle to a permanent value known as steady state. Still, further switching or circuit alteration is attempted. This brief spell of time is called transient time, and the value of the variables like current and voltage drops during this period is called transient value. Now, the transient response of series RL circuit. Now, let us consider a circuit. Let a DC voltage V be applied suddenly by closing the switch K. Applying KVL to the circuit, we are going to get Ri plus L di by dt equals to V. Di by dt plus I of R by L equals to V by L. This we can write P plus R by L of I equals to V by L. Let this be equation 1 and this be 2, where P equals to d by dt. Now, the equation number 2 is a non-homogeneous differential equation, and the solution is given by that I equals to IC plus IP, where IC is the complementary function given by that IC equals to C of e to the power of minus R by L of P, and that always goes to zero value in a relatively short time known as transient solution. And C being a constant here, IP is the particular solution of I that provides a steady state response and is given by IP equals to e to the power of minus R by L of T integral e to the power of R by L of T V by L of dt. Now let us solve this. E to the power of minus R by L of T. When you integrate this, you are going to get e to the power of R by L of T divided by the R by L, and which is multiplied by V by L. Then L gets cancelled. This term gets cancelled. You are going to get V by R. IP equals to. Hence, the net solution to get I is given by C e to the power of minus R by L from the complementary function of T plus V by R. Let this be equation number 3. An inductance, due to its electrical inertia, does not allow sudden changes of current through it following the rule of electromagnetic induction. Hence, the current through it just before switching is same to the current just after the switching. That represents that I at 0 minus is equals to I at 0 plus. However, before switching, there was no current through the inductor here. Hence, at the time of t plus, the current through the inductor will be 0. So, this equals to 0. With initial conditions, the equation number 3 becomes that 0 equals to C e to the power of minus R by L of T. T is 0 plus V by R. E to the power of 0 is equals to 1. So, this will be C plus V by R equals to 0. Then, from which C equals to minus V by R. This gives the current I, if you substitute in equation number 3, minus V by R e to the power of minus R by L of T plus V by R. Now take the V by R common, then you will be getting V by R of 1 minus e to the power of minus R by L of T, which is equals to I. This is in amps. Let this be equation number 4. The equation really shows that the exponential rise of current I charging the inductor. The profile of I as shown here. The time, this is I equals to V by R. This will be exponentially increasing. It may be noted that once the transient dies out within the short spell of time which can be observed by substituting the large value of t. The steady state current, that is final current, remains in the circuit is given by the value V by R. Now, it may also be observed that if we put t equals to L by R in the above equation, then the equation will become I equals to V by R of 1 minus e to the power of minus R by L. T is L by R, then I equals to V by R 1 minus e to the power of minus 1. Then I equals to V by R 1 minus e to the power of minus 1 equals to 0.368. I equals to V by R is the steady state current IS multiplied by 0.632 times. Let this equation number 5. IS being steady state current, that IS equals to V by R. Now, the equation number 5 means that at time t equals to L by R, the current through the RL circuit rises to 63.2% of the final value. Now, conventionally, this time is known as time constant. Inverse of time constant is called damping ratio, that is R by L. The voltage drop across the resistor and inductance during the transition period is given by voltage drop across the resistor is given by I into R, that equals to V by R. I value from the equation number 4. 1 minus e to the power of minus R by L of t multiplied by R. R gets cancelled. Then voltage drop across the resistor is given by V of 1 minus e to the power of minus R by L of t. The voltage drop across the inductor is given by L di by dt. That equals to L d by dt of V by R 1 minus e to the power of minus R by L of t. Let us solve this. L V by R. Now differentiating 1, you will be getting 0. So 0 minus of minus, so plus it will be e to the power of minus R by L of t multiplied by the R by L. L V by R, R by L e to the power of minus R by L of t. We'll be getting the voltage drop across the inductor is given by V E minus R by L of t. Now we observe that the voltage transient across the resistor is exponentially rising, while that across the inductance is exponentially decaying. Now obviously V R plus VL equals to V of 1 minus e to the power of minus R by L of t plus e to the power of minus R by L of t, which equals to the voltage V. Now, the instantaneous power in resistor and inductor are given by the power in resistor, which equals to voltage through the resistor multiplied by the current I, that equals to V 1 minus e to the power of minus R by L of t multiplied by V by R of 1 minus e to the power of minus R by L of t. Now let us solve this. We'll be getting V square by R of A minus B, which is nothing but A minus B whole square, that A square minus 2AB plus B square, that is E minus 2 R by L of t. Equation number 6. The instantaneous power in inductor, that is PL, is given by VL of I, that equals to VL is V e to the power of R by L of t multiplied by V by R 1 minus e to the power of minus R by L of t. Now we'll be getting V square by R, that is E R by L of t minus, I think we forgot the minus here, minus E minus 2 R by L of t. Let this be equation number 6b. Total instantaneous power P is given by PR plus PL. Now V square by R will take that common from both the equations, right hand side. then 1 minus 2 e to the power of minus r by L of t plus e minus 2 r by L of t plus e minus r by L of t, and this is square term, so minus e minus 2 r by L of t. This is plus term and this is minus term, gets cancelled. Then this one you'll be getting 1 minus e to the power of minus r by L of t multiplied by v square by r equals to the total power p. Now, until now we have seen the condition where series RL circuit is connected to DC voltage and the switch is closed so that the RL circuit can charge. Now analyze another transient condition of the RL circuit, assuming that following the closing of the switch the circuit reaches at steady state and suddenly the voltage is withdrawn by opening the switch and throwing to the point B from point A, which is discharging. Application of KVL to the circuit, then you will be getting Ri plus L di by dt equals to, after throwing it to the point B, the input voltage will become 0 as the voltage source is withdrawn by opening the switch. Now taking the I common and dividing with the L, then you will be getting R by L plus d by dt equals to 0, which is nothing but P plus R by L of I equals to 0. Let this be equation number 7. This is a homogeneous differential equation having only the complementary function and the particular function is 0. That means that I equals to IC plus IP, where IP equals to 0, then I equals to IC, which equals to C of e to the power of minus r by L of t. Let us differentiate the C constant here with the previous one by keeping C there. However, at the time t equals to 0 plus, the inductor will keep the steady state current, that is V by R, even the switch is thrown to the position B, short circuiting the charged RL circuit and withdrawing the voltage source. That means that I 0 plus equals to I st, that's steady state, of 0 minus, which equals to V by R. Let this be equation number 8. Now from the equation number 8, V by R equals to C dash e to the power of minus R by L of t is 0 in our case. That equals to C dash. Hence, the final solution for I equals to, the C dash is V by R e power minus R by L of t, which equals to, V by R is nothing but I naught e to the power of minus R by L of t. That is equation number 9. The decaying current is thus an exponentially decaying function, that profile being shown here with the time the current Ist equals to V by R will exponentially reduce. Now assuming the t value equals to L by R, then the equation number 9 will become that I equals to I naught e to the power of minus R by L multiplied by L by R, that is minus 1 e to the power of minus 1, which is nothing but 0.368 of I naught. L by R being a time constant, is observed that the decaying current will reach 36.8%, or else we can simplify this with 0.37 I naught, 37% of the initial steady state current at one time constant. Now the corresponding voltages across the resistance and inductance are given by VR equals to IR, that equals to V by R, this equation, e to the power of minus R by L of t multiplied by the resistance R will get cancelled. You'll be getting V e to the power of minus R by L of t, which is the voltage across the resistor. Now the voltage across the inductor VL is given by L di by dt equals to L d by dt of V by R e power minus R by L of t. Now to solve this, L V by R by L of e to the power of minus R by L of T. Voltage across the inductor VL is given by minus V. Here we have minus, so this will come here. E to the power of minus R by L of T. The instantaneous powers, that is PR, is given by, that is VR into I. That equals to this one multiplied by this one, that is V square by R e to the power of minus 2 R by L of T. This is in watts. The instantaneous power in inductor is given by VL I. That equals to this one multiplied by this one. That is minus V square by R e to the power of minus 2 R by L of T. This is in volt amps, as this is a reactive power. This is regarding the transient response of a series RL circuit for DC voltage source in two cases. One is charging and the one is discharging. If this video is useful, please like, share and subscribe.